Probability in Stats Lesson 3 is independent and dependent events. One thing we're going to be talking a lot about in this unit is ways to visualize probability representations, and one of them is a tree diagram. So a tree diagram is a way to represent possible outcomes in an event where each branch represents a combined event. So for example, let's say you're going to flip a coin twice. So the first flip, you have two possible outcomes, heads or tails. The second flip, regardless of whether you flipped heads or you flipped tails, you'll have two possible outcomes, heads or tails. In this case, the probabilities are all the same because flipping a coin is not going to change. But it's a nice way to show like successive choices or successive events. We're also going to be using some set theory notation in this unit. So here's a table of kind of the main ones we're going to be using. The first one is intersection. Intersection is the math word for and. We use a little upside down U here. It kind of looks like an A for and. So this is saying A intersect B, or A and B, and that means that events A and B are both occurring at the same time. Union, which we use the U for, A union B, it means or, so A or B. It means events A or B or both of them are occurring. The complement is a little apostrophe. Sometimes you'll see a little tiny C up here, but most of the time it's an apostrophe, and it means not A. So everything except for event A. And then the last one we're going to talk about is conditional. So this is saying A given B. This bar means given. So it's event A happens knowing that event B has already happened. Independent events are events in which the occurrence of each event does not affect the probability of another event happening. The way that we can calculate the probability of both events happening at the same time, if they are independent, is we can just multiply each of their probabilities by each other independently. So independent events would be like flipping a coin and rolling a die. The flip does not affect the roll. Pulling marbles out of a bag, if you replace the marbles after each pull, those would be examples. Dependent events are events in which the occurrence of one event does affect the probability of another event happening. In order to calculate an intersection of two events that are dependent, we multiply the probability of the first one by the probability that the second occurred, given that the first has already occurred. A common example of a dependent event would be pulling marbles without replacement. So because we're not putting the marble back, the probability of the next one has been affected by the previous pull. Conditional probability, the probability that B event occurs given that event A has already occurred. So probability of B given A. It's the probability of them both happening, probability of A and B, divided by the probability of whatever the given one is happening. So given that your first marble is green, what's the probability that the second marble is blue? So we want the first one to be green and then the second one to be blue, divided by the probability that we knew the first one was green. A six-sided die is labeled with the numbers 1, 2, 2, 3, 3, and 3. 4 sides are colored red, 1 side is white, and 1 side is yellow. Find the probability that you toss a 2 and then another 2. Rolling a fair die is independent of any successive roll. So each time I roll, it does not affect the next roll. So when we find the probability that I toss a 2 and then a 2, I can think of them as independent events. So because they're independent, I can multiply each of the two individual probabilities together, and that will give me my overall probability. So the probability of rolling a 2, there are 2 2s out of 6 possible outcomes. So it's a 2 out of 6, and then regardless of what happens on the first one, the probability that I roll a 2 on the next one is also going to be 2 out of 6. So I end up with 4 out of 36, or 1 out of 9. So go ahead and pause the video and find the probability that you toss a red, and then a white, and then a yellow. So again, rolling the dice are independent of each other, so each roll does not affect the next. So if I want to find the probability of a red, and then a white, and then a yellow, I'm going to find the probability of the red, multiply by the probability of white, and then multiply by the probability of yellow. 4 sides out of the 6 are red, 1 out of the 6 is white, 1 out of the 6 is yellow. So I end up 4 possibilities out of 216 possible rolls, or 1 out of 54. A standard card deck contains 4 suits, red hearts, red diamonds, black spades, and black clubs, of 13 cards each. So each suit contains an ace, the numbers 2 through 10, and then 3 face cards, a jack, a queen, and a king. 2 cards are randomly selected from the deck. Find the probability of each. The first one says, find the probability that 2 hearts are pulled when the first card is replaced. This is similar to the problem that we just did because when you replace cards, they're independent events. I've reset the full deck when I replaced it, so it starts over. I'm going to skip that one first, and I'm going to jump to the second one. Now it's saying 2 hearts when the first card is not replaced. So that's a key piece here. When it's not replaced, they're no longer independent events. So the problem is that when I go to pull the second card, my probability have now changed. So I need to keep that in mind. So when I go to find the probability of a heart, and then a heart given that I've already pulled a heart, I'm going to find the probability of the first heart, and then I'm going to multiply it by the probability of the second heart given that the first one is already a heart. So for the first one, I know that there are 13 hearts in the full deck of 52 cards. So for the first probability, it's just going to be 13 out of 52. For the second one, I have to think about what just happened. So I just pulled 1 card out of the deck and didn't replace it. So now my total is down to 51. And if we assume that one of those was a heart, my total number of hearts have gone from 13 down to 12. So my probability of the second card being a heart has changed because I didn't replace that first card. So if I multiply these together, I end up with 156 out of 2,652. So there are 2,652 ways to pull 2 cards out of a deck without replacement, and 156 of those ways are 2 hearts. If I simplify that, it's 1 over 17 or 0.0588. So now go ahead and pause the video and try 1 and 3. For the first one, if I'm pulling 2 hearts with replacement, they are independent events. So the first heart is 13 out of 52. I replace it, so my deck has been completely reset. So my second heart is again 13 out of 52. So if I multiply that together, I get 169 possible 2 hearts out of 2,704 total possible ways of picking 2 cards with replacement. For number 3, I want the probability of a queen and then not replacing it, and then a king. So I want the probability of a queen and then the probability of a king given that I've pulled a queen. So for the first one, there are 4 queens out of the 52 cards. For the second one, I didn't lose a king, so I still have 4 kings, but I do have 1 card in my pocket, so there's only 51 total cards. So I end up with 16 out of 2,652. A box in an electronics store contains 9-volt batteries of different colors. There are 5 red, 6 blue, and 7 orange. 2 batteries are chosen to power up a radio that requires 2 batteries. So the key piece is that you need to have both of those 2 batteries in your hand at the end. So is this situation independent or dependent, and why? So because we need to have both of those batteries in our hand, this is a non-replacing situation. So we take 1 battery out, we don't replace it, and we pick another one. So because of that, this would be a dependent situation because the first outcome is affecting the second's probability. So now we want to draw a tree diagram that represents this situation. So again, when we think about a tree diagram, we're thinking about consecutive choices and then showing the probabilities on there of all of the different possibilities. So here's what a tree diagram would look like for the situation. So for the first battery, we have 3 options: red, blue, or orange. And I wrote out the probabilities out of 18 total batteries for each of those options: 5 out of 18 for red, 6 out of 18 for blue, 7 out of 18 for orange. For the second one, regardless of what we chose for the first battery, we still have 3 choices: red, blue, and orange. But the probability of our first one is now affecting our second one. So for example, all of the denominators have now decreased by 1 because we have 1 battery in our hand. In the box, there's only 17 batteries. If the first one was red, my red is going to decrease by 1, and it's going to be 4 out of 17. Blue and orange are not going to change. If the first one's blue, red and orange don't change, but blue decreases by 1. If it's orange, red and blue don't change, but orange will decrease by 1. So now you can use this tree diagram to help you find the probability of whatever you want. So go ahead and use the tree diagram to help you find the probability that both of the batteries are different colors. So I did this in kind of 2 different ways. The first way is I thought about it literally being different batteries, so each subsequent choice would have to be different. So I thought about all the combinations that could be and added them up. So it could be red and blue, it could be red and orange, blue and red, blue and orange, orange and red, orange and blue. And each of these, this is a conditional probability. We already adjusted for that in our tree diagram, so I can just multiply them together. So I multiplied each of those together, add them all up, and got 306 possible ways you can pick 2 batteries, and 214 of those are different. The other way I thought about it was I thought about being different is the complement or the opposite of being the same. So the probability of them being different was 1 minus the probability of them being the same. And there's only 3 ways they can be the same, red and red, blue and blue, orange and orange. So then I added those ones up and subtracted from 1. So a slightly simpler calculation if you can keep in mind that complement. Mark buys his t-shirts from exactly 2 suppliers, 2AT and Netsshirts, and he only buys 2 colors, gray and blue. He buys 73% of his shirts from 2AT, and 16% of his 2AT shirts are gray, and 80% of his Netsshirts are gray. So we have a tree diagram here, so complete the tree diagram with the missing pieces of information. Calculate the probability that a t-shirt randomly chosen by Mark one morning is gray, and then given that Mark chooses a gray t-shirt, determine the probability it was supplied by Netsshirts. So there's 2 ways that he can have a gray shirt. It can be a 2AT shirt and gray or a Netshirt and gray. So I calculated each of those probabilities and added them up. So the probability of it being 2AT is 0.73, and then the probability of it being blue, given that it's 2AT, is 0.16, and then the probability of it being a Netshirt is 0.27, and the probability of it being gray, given it's a Netshirt, is 0.8. So added that together, I got 0.3328. For a given probability, it's the given probability that they both happen divided by the probability of the given. So we want the probability that it's a Netshirt given that it's gray. So we want the probability that it's a Netshirt and gray divided by the probability that it's gray. So I took the Netshirts and gray, multiplied them together to get the and then divided by the probability of it being gray, which we found in part 2, and got 0.649. So independent events are events that do not affect each other. Dependent events affect each other. To find the probability of an and, you multiply together. If they are dependent, you have to make sure that the second event or third event or how many ever events is the conditional probability given that the first event has already happened. And then conditional probability, it's always the probability of the and divided by the probability of the given.